THHN wire is often marked with both THWN-2 or THHN. This marking signifies that the wire is suitable for use in wet locations. The letter W within the THWN designation is an indicator that the wire is designed to withstand moisture in damp environments. The letter N indicates that the insulation is constructed using nylon. Nylon provides enhanced resistance against moisture, abrasion, and various chemicals. The 2 in THWN-2 signifies that the wire is rated for a maximum operating temperature of 90 degrees Celsius. This characteristic of THHN wire permits its application in locations where exposure to moisture is anticipated, such as outdoor areas, bathrooms, and kitchens. THHN wire is also appropriate for use within conduits, raceways, and other enclosed spaces where direct sunlight exposure is minimal. Therefore, when selecting wiring for environments with potential moisture exposure, the THWN-2 or THHN marking is a key indicator of its suitability for such applications. It is always important to consult local electrical codes and regulations to ensure proper wiring practices. Selecting the correct type of wire ensures safety and compliance. Understanding the markings on electrical wire is crucial for safe and effective installations. THHN wire offers versatility, being usable in both dry and wet locations due to its construction and insulation properties. Factors like ambient temperature and the number of current-carrying conductors influence the ampacity of conductors as outlined in the National Electrical Code, specifically Table 310.15b16 and subsequent tables. This table provides ampacity ratings for various conductor types based on insulation temperature rating and installation conditions. For example, a THHN conductor with a 90 degrees Celsius insulation rating might have a higher ampacity than a conductor with a lower temperature rating, assuming all other factors are equal. However, the termination temperature limitations of connected equipment often dictate the actual ampacity that can be used. Most electrical equipment is rated for 75 degrees Celsius terminations, even if the conductor is rated for 90 degrees Celsius. In such cases, the ampacity of the 75 degrees Celsius column in Table 310.15b16 must be used. Correction factors are applied when the ambient temperature exceeds 30 degrees Celsius as detailed in Table 310.15b2. These factors reduce the allowable ampacity of the conductor to prevent overheating. For instance, if a conductor is installed in an ambient temperature of 40 degrees Celsius, a correction factor less than 1.0 must be applied to the ampacity listed in Table 310.15b16. Adjustment factors are applied when multiple current-carrying conductors are bundled together or installed in close proximity as per Table 310.15b3. These factors account for the increased heat generated by multiple conductors, which can reduce the overall ampacity. For example, if 6 current-carrying conductors are installed in a single conduit, an adjustment factor of 0.8 is applied to the ampacity listed in Table 310.15b16. Conduit fill limitations, as specified in Chapter 9 of the NEC, restrict the number and size of conductors that can be installed in a conduit. These limitations prevent overcrowding, which can lead to overheating and insulation damage. The allowable fill percentage varies depending on the type and size of the conduit. Voltage drop is another critical consideration in conductor selection, especially for long circuit runs. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Voltage drop can be calculated using Ohm's law and conductor characteristics such as resistance and length. Conductor resistance varies depending on the material, size, and temperature of the conductor. Copper conductors typically have lower resistance than aluminum conductors of the same size. Larger conductors have lower resistance than smaller conductors. Conductor impedance, which includes both resistance and reactance, also affects voltage drop. Reactance is more significant in alternating current AC circuits and is influenced by factors such as conductor spacing and frequency. Grounding conductors, as outlined in Article 250 of the NEC, provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. Grounding conductors can be bare or insulated and must be properly sized according to the size of the ungrounded conductors. Equipment grounding conductors connect the non-current carrying metal parts of electrical equipment to the grounding system, preventing shock hazards. Bonding jumpers connect different parts of the grounding system together, ensuring electrical continuity. Ground fault circuit interrupters, or GFCIs, protect against electrical shock by detecting ground faults and quickly interrupting the circuit. GFCIs are required in locations where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or RFCIs, protect against fires caused by arcing faults in electrical wiring. RFCIs detect abnormal arcing conditions and de-energize the circuit, preventing the arc from igniting nearby materials. Surge protective devices, or SPDs, protect against voltage surges caused by lightning strikes or other electrical disturbances. SPD divert the surge current to ground, preventing damage to sensitive electronic equipment. Overcurrent protection devices, such as circuit breakers and fuses, protect against overloads and short circuits. Circuit breakers are resettable devices that trip when the current exceeds a predetermined level. Fuses are one-time use devices that melt and interrupt the circuit when the current exceeds a predetermined level. Short circuit current rating, or SCCR, is the maximum fault current that an electrical component or system can safely withstand. Electrical equipment must have an SCCR rating that is equal to or greater than the available fault current at its point of installation. Available fault current is the maximum current that could flow in a short circuit condition. It is determined by the characteristics of the power source and the impedance of the circuit. Series ratings allow the use of overcurrent protective devices with lower SCCR ratings if they are installed in series with other devices that provide additional protection. Selective coordination ensures that only the overcurrent protective device closest to the fault opens, minimizing disruption to the rest of the electrical system. Maintenance and testing are essential for ensuring the continued safe and reliable operation of electrical systems. Regular inspections can identify potential problems before they lead to failures or hazards. Testing can verify the proper functioning of overcurrent protective devices, grounding systems, and other critical components. Infrared thermography can be used to detect hotspots in electrical equipment, which may indicate loose connections or other problems. Power quality monitoring can identify voltage sags, swells, and other disturbances that can damage sensitive electronic equipment. Energy efficiency is an increasingly important consideration in electrical system design and operation. High-efficiency lighting, motors, and other equipment can reduce energy consumption and lower operating costs. Power factor correction can improve the efficiency of electrical systems by reducing reactive power. Demand response programs can help reduce peak demand by shifting energy consumption to off-peak eras. Renewable energy sources, such as solar and wind power, can provide clean and sustainable electricity. Electrical safety training is essential for all workers who work on or near electrical equipment. Training should cover topics such as hazard recognition, lockout/tagout procedures, and personal protective equipment. Lockout/tagout procedures are used to de-energize electrical equipment before it is worked on, preventing accidental energization. Personal protective equipment, or PPE, such as gloves, safety glasses, and arc-rated clothing can protect workers from electrical hazards. Safe work practices such as maintaining safe distances from energized equipment and using insulated tools can reduce the risk of electrical accidents. The National Electrical Code, or NEC, is a widely adopted set of standards for the safe installation of electrical wiring and equipment. The NEC is updated every 3 years to reflect changes in technology and industry best practices. State and local jurisdictions may adopt the NEC or modify it to meet the specific needs. Electrical permits are required for most electrical installations to ensure that the work is performed in accordance with the NEC and local codes. Electrical inspections are conducted by qualified inspectors to verify that the installation meets the requirements of the NEC and local codes. Continuing education is important for electrical professionals to stay up to date on the latest technologies and code changes. Certifications, such as those offered by the National Institute for Certification in Engineering Technologies, or NICET, can demonstrate competence and professionalism. Professional organizations, such as the Institute of Electrical and Electronics Engineers, or IEE, and the International Association of Electrical Inspectors, or IE, provide resources and networking opportunities for electrical professionals. The design of electrical systems involves many complex calculations and considerations. Load calculations are used to determine the size of service entrance conductors, feeders, and branch circuits. Short circuit calculations are used to determine the available fault current and to select overcurrent protective devices with adequate SCCR ratings. Voltage drop calculations are used to ensure that voltage drop is within acceptable limits. Coordination studies are used to ensure that overcurrent protective devices are selectively coordinated. Grounding studies are used to design effective grounding systems. Lighting design involves selecting appropriate lighting fixtures and calculating illumination levels. Power systems studies, such as load flow studies and stability studies, are used to analyze the performance of electrical systems under various operating conditions. Automation and control systems are used to monitor and control electrical equipment. Programmable logic controllers, or PLCs, are used to automate industrial processes. Supervisory control and data acquisition, or SCADA, systems are used to monitor and control remote electrical equipment. Building automation systems, or BAS, are used to control lighting, HVAC, and other building systems. Data centers require reliable and efficient electrical systems to support critical IT infrastructure. Uninterruptible power supplies, or UPSs, provide backup power in the event of a power outage. Generators provide emergency power for extended outages. Power distribution units, or PDUs, distribute power to individual servers and other equipment. Cooling systems are used to remove heat generated by the IT equipment. Monitoring systems are used to track power consumption and environmental conditions. Healthcare facilities require especially reliable electrical systems to support life-saving equipment. Emergency power systems are required to provide backup power in the event of a power outage. Isolated power systems are used in critical care areas to protect against electrical shock. Redundant power systems are used to ensure continuous power supply. Operating rooms and intensive care units have stringent electrical requirements. Industrial facilities require robust electrical systems to power heavy machinery and equipment. Motor control centers, or MCCs, are used to control and protect electric motors. Variable frequency drives, or VFDs, are used to control the speed of electric motors. Power distribution systems are designed to minimize downtime and ensure reliable power supply. Hazardous locations, such as those containing flammable gases or dust, require special electrical equipment and wiring methods. Explosion-proof equipment is designed to contain explosions within the enclosure, preventing them from igniting the surrounding atmosphere. Intrinsically safe equipment is designed to operate at low voltage and current levels, preventing the formation of sparks or hot surfaces. Purged and pressurized systems are used to create a safe environment by removing or diluting hazardous substances. Renewable energy systems, such as solar photovoltaic, or PV systems and wind power systems, are becoming increasingly common. Solar inverters convert direct current, or DC, electricity from solar panels to alternating current, or AC, electricity. Wind turbines convert wind energy to electrical energy. Energy storage systems, such as batteries, can store excess energy for later use. Smart grids integrate renewable energy sources and improve the efficiency and reliability of the power grid. Microgrids are localized energy grids that can operate independently of the main power grid. Electric vehicles, or EVs, are becoming increasingly popular. Charging stations are required to provide electricity to EV. Battery management systems, or BMS, monitor and control the charging and discharging of EV batteries. The design and installation of electrical systems is a complex and challenging field that requires a thorough understanding of electrical theory, codes, and standards. Continuing education and professional development are essential for electrical professionals to stay up to date on the latest technologies and best practices. By following safe work practices and adhering to the NEC, electrical professionals can help to ensure the safe and reliable operation of electrical systems.